Okay, so in this lecture, I'm going to talk about this SPM techniques, which is the last type of techniques we are going to discuss under the characterization techniques available for nano characterizations. So SPM stands for scanning probe microscopy. So these are a family of instruments used to study surface properties of materials from the atomic to the micron level. And SPM, as the name itself says, it has a probe which scans the sample. So the given schematic diagram below will show you some commonly available components in every SPM. So we have a probe tip which will scan over the sample. Sample is mounted on the sample stage, and then sample stage is mounted on a piezoelectric scanner which will move the sample under the tip, or the tip will move over the sample in a raster pattern, right? So this piezoelectric means when you apply a pressure, that it will generate some current which will be connected to a computer system that drives the scanner, measures data and converts the data into an image. Then there's the feedback loop system to control the vertical position of the tip or the stage. Right, we will be discussing these things later in more details. The scanning probe microscopes work differently compared to the optical microscopes, because in the optical microscope, you can view the sample. The operator have a direct view of the sample, but in the SPM techniques, the operator does not have a direct view. Like even in the SEM, TEM, the signals were generated, the generator signals were converted to an image, but in this SPM, you don't have that direct view of the surface, but an image that represents the structure of the surface is all there for the operator to weave. They are very powerful and can have very high resolution, up to a single nanometer. This is so far, I think, scanning tunneling microscopy, which comes under scanning probe microscopy category, has the highest atomic resolution to date. Right, so we'll talk a little bit about the history of this SPM. The first member of the scanning probe microscopy is the STM, or we say scanning tunneling microscopy, which was developed in 1980s. The optical microscope were the first type of microscopes that were developed and used for scientific research, but it was soon discovered that there was a limit to their capabilities, because when we try to view specimens smaller than the wavelength of the light, image becomes blurry or distorted due to the diffraction happening. Therefore, they looked into a source other than light source, which can generate with a source with where they can use to image with much lower wavelength, and the electron microscope was developed to overcome this limitation in around 1921, which used the beam of electrons to create an image of the sample, and this allowed significant increase in the resolution of the microscopic images that are being created. Then later, scanning probe microscopy was developed around 1980s to allow the investigation of surfaces with atomic resolution. Now that is beyond the capability of electron microscope. So the pioneering couple was Dr. Gerd Binnig and Dr. Heinrich Rohrer, invented the first scanning tunneling microscope in 1981. And this was a significant breakthrough in the field of nanotechnology because it allowed scientists to weave a representation of the surface of samples at an atomic level. It is now possible for scientists to weave individual atoms, and they can study the properties and manipulate them to create new structures using these scanning probe microscopies. And they received Nobel Prize in Physics 1986 for the invention of this scanning tunneling microscope. Right, so in brief, how the SPM generates the image. They use a tip that will raster scan in X and Y direction, and it has a Z modulation or height modulation by feedback system. We will come into it later in more details. So if we talk about the scanning probe microscopy family, there are several different types of scanning probe microscopes, including scanning tunneling microscope, that will based on the tip sample electrical current. STM has the highest resolution so far and operated at ultra high vacuum. Scanning probe microscopy, second type is the AFM or the atomic force microscopy, which is, I think, far more familiar to you. So that measures the, there's the tip sample interaction. It measures the electrostatic force between the tip and the specimen. So it's basically a mechanical force. Under AFM, we will have magnetic force microscope, which measures the magnetic force between the tip and the specimen. And then we have the latest technology, which is near field scanning optical microscope, which combines AFM with optical microscopy. It uses a laser directed into the ensom using a glass fiber, and you combine AFM with optical microscopy. So this contradicts my previous statement, says that the viewer cannot directly observe the sample, but in the ensom you can, because it has the optical microscopy component into it. Ensom is a bit a complicated section, which I'm not planning to do in details, but you can read if you want to. Right, so how does this STM work? So what are the basic components of scanning tunneling microscope? So here we have a scanner that can be mounted with a tip or the sample stage. Let me find whether I can change this arrow. I will go for hand tool. Yeah, here. The scanner can be mounted with a tip or the sample stage. We have a piezoelectric tube with electrodes attached. So we have the tip. So this is STM, scanning tunneling microscope. So we have the tip and we have the sample, and we lower this tip very, very close to the sample, such that now the distance between the tip and the sample is few nanometers. Like, it's more close to few angstroms, but then what happens when they are closer together, electrons will either starts tunneling from tip to the sample or from sample to the tip, depending on the situation. And this tunneling current is imaged, recorded, and used to image the surface of the sample. So 5 basic components the STM has is metal tip, piezoelectric scanner, current amplifier, biopotentiostat or the bias, and feedback loop, which provides the current. So the scanning probe microscope has a sharp probe tip on the end of cantilever, excuse me, which can scan the surface of the specimen. And the tip moves back and forth in a very controlled manner, and it is possible to move the probe atom by atom. Force deflects the cantilever when the tip gets closer to the surface of the sample, and it can be measured by a laser reflected from the cantilever into photodiodes. So there are so many different forces that may cause the deflection, such as mechanical forces, electrostatic, magnetic, chemical bonds, van der Waals, capillary forces, likewise so many forces. The data from the laser reflections can be detected by photodiodes that is combined to generate an image by the computer. The image has actually no color because it is just a representation of the properties rather than the light. But we artificially give them false colors to, it is easier for the observer to differentiate the different properties of the specimen. Right. So here the STM should be conducting because we measure the current tunneling from tip to the sample or from sample to the tip. Definitely both the sample and the tip should support current conduction. Therefore, the SPM tip as well as the sample should be conducting. And STM plays with the very top atom of at the tip and the nearest atom on the sample. So the whole tip is not necessarily very sharp in shape. Now, this is very different from the case of the AFM, where the spatial contact is very, very crucial for the feedback. But in the STM, you don't need to have very sharp, like the tip doesn't have to be sharper from the beginning to the end. Only that if you take a wire and cleave it using a knife, you will be able to get a sharpened wire with one tip at the edge. So how do we obtain these wonderful tunneling tips where only one atom is at the end of the tip? You can easily obtain it simply by cutting a thin metal wire using a wire cutter, right? So there's always a single atom left over at the very end of the tip. And as I told you, this uses scanning tunneling microscope. Tunneling means it measures the tunneling current. So tunneling current is a result of the overlap of the tip and the sample electron wave function. So the basic requirement for this tunneling current to observe is you need to have a very small distance between the specimen and the tip, so that the electron function can penetrate, can overlap and then easily detected, and you need to bias. Because we know the Fermi energy level, the work function is there, you need to play around so that the net current flow is either flowing from tip to the sample or from sample to the tip. Right. So in a metal, the energy levels of the electrons are filled up to a particular energy known as the Fermi energy. So if it is not biased, if it is not heated, in a natural environment, the energy levels of the electrons are filled up to Fermi energy level, or EF in simple terms. So in order for an electron to leave the metal, it needs an additional amount of energy, what we call the work function. So work function is, now we have the specimen here, electrons are filled up to EF, and then we have the vacuum energy level. So if the electron wants to leave the specimen into, that means it gets into the vacuum, it needs to overcome this barrier. So overcoming this barrier means it needs to gain the energy. We call it the work function. So if you supply the specimen with this EF, you can get the electrons overcome this barrier and come out of the atoms into the vacuum. Right. When the specimen and the tip are brought closer to each other, there is only a narrow region of empty space left between them. So you take the specimen here, you have the tip. If they are made up of the same material, then no problem. Their Fermi energy levels are in the same level, but there is a gap. Usually we use the ultra high vacuum here. So the gap between these two is very small, but it is filled with vacuum. So in order for the electron from the specimen to go out and travel to the tip, either we need to supply the a current, and we need to bias it. Like bias means by supplying some, if we supply some current to the tip or the potential difference to the tip, we can lower the Fermi energy level of the tip. Because when they are like in the same energy level, they can't go and fill, because because already the electrons are filled up to the Fermi level. There's no space for this. If you release, if you somehow release some electrons from the specimen, and if you want it to go to the tip, there's no energy. I mean, there's no spots, vacancies left for this electron to go and occupy. So to do that, first you need to supply some positive potential for the tip, so that you can lower the Fermi level of the tip. And that by lowering the Fermi energy, you can see there is a vacancy created. Not vacancy, it is actually this. If you remove this electron can go and occupy in this space, right? So you create a space for the incoming electrons to come and stay. But if the distance between the specimen and the tip is small enough, electrons, they don't need to have the work function, or the work function is a very high energy required, but it doesn't need that. They can simply tunnel through this barrier and occupy in that space created by biasing the tip. Right. When a voltage V is applied between the specimen and the tip, tunneling effect results in a net electron current. In this example, the electron will flow from specimen to the tip, and that is the tunneling current. Or you can bias the sample or the specimen and create the space necessary for the electrons from the tip to tunnel through and get occupied in that space. So you can bias the specimen. In that case, electrons tunnel from the tip towards the specimen. That is the tunneling current coming from tip to specimen. Either way is possible here. That depends on your sample, on your situation, and how you bias it. So electron density of states and Fermi level in a more friendly schematic way. So when the sample is at a normal condition, electrons are sitting up to until Fermi energy level. So if you want to get an idea about the density of states of energy, or we call it DOS, you define delta E, and then you draw a strip, and then you try to calculate how many smileys are sitting inside this strip. So if you know that, you now here I think it is around, we have 1, 2, 3, 4, 5, 6, 7. 7 electrons are sitting here. So you said now density of states here for that defined delta E or epsilon here is, that is the density of state is 7 electrons. So electrons fill up the energy valley in the sample until there's no more electrons, and top energy level at which the electrons sit called the Fermi energy level. So electrons are filled up to that level. High field energy is the Fermi energy level. For every energy epsilon, the density of states is the number of electrons sitting within that delta E of the epsilon divided by epsilon. So far, for the energy shown in the previous schematic, as I told you, the delta E is represented by that blue strip. The density of states is approximately 7 electrons per delta E. Now we counted, and roughly it was around 7 full electrons were sitting inside that blue strip. So it is approximately 7 over delta epsilon. Right. Now, this is the case where you have the sample and the tip closer together. There's a very small distance between them, and it is kept under high vacuum. So you have the sample, you have the tip, both are filled up to Fermi energy levels, but they are separated by the vacuum barrier. So if the electrons from the sample wants to go to the tip, then the electrons will have to obtain that needed work function energy to climb up the vacuum barrier and go to the other side, right? Electrons are happily sitting in either in the tip or on the sample. They are sitting in nice energy valleys, right? It takes energy to remove an electron into free space because they are happily sitting. There's an inertia for them to go out from the sample. So you need to supply that energy to break it free from the sample or from the tip. So we can think of the vacuum around the tip as an energy hill that the electrons would need to climb in order to escape. The height of this energy hill is called the work function, or pi. In order to bring an electron up and over the vacuum barrier to the tip from the tip into the sample, or from the sample to the tip, we would need to supply that very large amount of energy called work function. But climbing hill is a hard work. They are reluctant to do that. But luckily, quantum mechanics allows these electrons to tunnel right through the barrier. And you need to keep that in mind. This only works for particles with both and wave particle characteristic, but not for macroscopic objects, right? So that's why we can't walk through a wall. Right, so these are, we can apply them for microscopic or very small particles which can behave. This is also relativistic, but these particles can behave as waves as well as particles. Now, electron is we consider as a particle, but when they're highly accelerated, they behave as waves. Right. So as long as both the tip and the samples are held at the same electrical potential, their Fermi levels are lined up exactly. Now, as I told you, when their Fermi levels are lined on the same level, there's no empty states on either side available for tunneling into. So even the electrons are willing to tunnel through this barrier, they can't go and sit on the other side because there's no space for them. So that's why we use a bias voltage between the tip and the sample. Whenever you apply a positive potential, you can lower the Fermi energy. So here you have the sample, you have the tip, and you have the vacuum barrier. Now here what you do, you apply a bias voltage to the sample with respect to the tip, and we effectively raise the Fermi level of the sample with respect to the tip. Now you have the bias voltage. So by applying the bias voltage, what you do, you will lower the Fermi energy level by EV. So you apply a voltage to the sample, thereby making it higher. So now you can see we have created the space here between the EF and the EF of the tip. Because it is lowered now, there is a vacancy, there's a space for the tunneling electron to go and occupy. Under the bias voltage, electrons will happily move, tunnel through this vacuum barrier into the tip. So this tunneling current happens when a thin metal tip is brought in close proximity of the sample surface. At a distance only few angstroms, this will be successful. So you can see how closely they are situated. The overlap of the tip and the sample electron wave function is large enough for electrons to tunnel to occur, right? If the distance is too great, like let's say like angstrom level, nanometer level, then this is not going to happen. Then we supply an electric voltage between the sample and the tip, and this tunneling phenomenon results in a net electrical current we call the tunneling current. This current depends mainly on the tip to surface distance, very crucial, D, and on the bias voltage, V, and on the height of the barrier. That is, the barrier means the work function. This approximate equation shows that the tunneling current obeys Ohm's law, right? That is, the current is proportional to the voltage. The current depends exponentially on the distance. So if we look at the current and the distance, you can see that depends on exponentially. So if you convert it to an equation, you can see the I, which is a function of distance, is constant times EV, and there's an exponential term which will define the current distance relation. So when we move away, you can see the current is drastically dropping, and the current depends exponentially on the distance. And for a typical value of the work function of 4 electron volt for a metal, the tunneling current reduces by a factor of by a factor 10 for every 0.1 nanometer. So if you increase it by 0.1 nanometer, that is 1 angstrom, you will decrease the tunneling current by factor of 10. So you can see how sensitive it is, the distance. So that means over a typical atomic diameter, that is around 0.3 nanometers, the tunneling current changes by a factor of 1,000. So this is what makes the STM so sensitive, and we can use it in high resolution imaging. The tunneling current depends so strongly on the distance that is dominated by the contribution flowing between the last atom of the tip and the nearest atom in the specimen. So this capables us doing the single atom imaging, right? So these are some common work functions for common metals. Like for silver, it is around 4.26 electron volt. For gold, it's around 4.8 electron volt, right? Scanning resolution of a scanning tunneling microscope. In the macroscopic scale, you have the tunneling. This is the tip we loaded onto the scanner, and we have the tunneling voltage, which will be applied to either to the tip, between the tip and the sample to bias them. And in the atomic scale, you can see that the interaction happens between the tip and the sample, either current from the sample to the tip or from tip to the sample. But in this case, the positive field is given to the tip. That means you have created the space here, so the electrons can current will flow, electrons will flow the other way, and that means the current is generated from the sample towards the tip. SEM does not probe the nuclear position directly, but rather it probes the electron density, that is the size of the whole atom, right? So when it keeps on scanning, what happens if there's a different material, that means there's a different atom. So electron density is different, there will be a difference in the current created. So that the small difference in the tunneling current will provide you information about the material or the strange atom that is located in the homogeneous medium. And if you do not have a smooth sample, now here you have a single plane of atom, but here you can see there is a step. Likewise, when you move your tip towards your sample, the distance between the tip and the sample will be different. So when the tip to sample uh, uh, distance is lowered, what happens? The current is exponentially intensified. So that change in the current or increase in the current will tell you encountered a step. Or if there's a valley, that means the distance is increased. That means there's an exponential decrease in the current. So that will tell you that you encountered a valley. So these are the sensitive information that can be used to generate the image. So principle of scanning tunneling microscope: applying a negative sample voltage yields electron tunneling from occupied state at the surface into unoccupied states of the tip. So you lower the tip Fermi energy level by creating a space there. You can let the tunneling electrons from sample to the tip to go and occupy there. So that creates a tunneling current. Keeping the tunneling current constant while scanning the tip over the surface, the tip height follows the contour of constant local density state. So if it encounters a different atom with that means the different electron density, that will create a change in the current. So if you if the current is increased, now here what it says, keeping the tunneling current constant. So if you feel that the current is higher, what you will do, you will adjust, you will slightly increase the distance so that the current is again reduced back to the constant level. So just by encountering a different atoms, you will see, if you just image the tip path, you will see, oh, okay, there was this current increase due to a different atom, and using a feedback loop, this will provide you with some using the feedback loop, you can lower or increase the tip height. Right. Tip height follows a contour constant local density of state. So if you just follow that contour, like this contour here, it is following a constant local density of states. Right. So constant height mode, there are two modes, basically constant height mode and constant current mode. Now it is in the constant height mode, imaging the different surface atoms due to their different work functions will reveal the surface compositions of defects. But in the constant height mode, it is very important for you to have a very smooth surface, homogeneous, like smooth surface. Even though it consists of different materials, like different atoms distributed in different locations, that's okay. So because if you have a height difference, that will, like, you won't be able to say whether this current difference is occurring because of the different atom, because it has a different electron density or different height. So in the constant height mode, it's better for you to have a smooth surface. In the constant current mode, will tell you heights for the same atom. So this is better for you to have a not so smooth sample, but with a homogeneous medium. So imaging the surface topography at atomic resolution, if the surface is composed of the same atom. So if you know that your sample is composed of the same material, you don't have much impurities in it, the only factor affecting the tunneling current is the distance between the tip and the sample. Therefore, if you realize that there's a sudden increase in the tunneling current, that means you have encountered a step. So in the constant current mode, what you will do, you will give now you know that in the constant current mode, your constant current is somewhat different because you encountered a step. feedback loop will automatically increase the height of the tip. What I mean is lowering. It will take up the tip so that you can go to that distance where you can achieve the constant current. And again, if you encounter a sudden decrease in the constant current, that means you encountered a valley. The feedback loop will lower the tip to maintain the constant current. So if you just get that contour of that tip movement, you can get the topographical idea about the sample. So brief overview of the scanning tunneling microscope. In the scanning tunneling microscope, the sample is scanned by a very fine metallic tip. The scanning can be controlled in 3 dimensions by using a piezo scanner, either bound to the tip or attached to the sample stage. Sample is positively or negatively biased so that the small current or the tunneling current flows either from the sample to the tip or from tip to the sample when the tip is in close proximity to the sample. So this feeble tunneling current is amplified and measured and used in imaging. With the help of the tunneling current, the feedback electronics keeps the distance between the tip and the sample constant. If the tunneling current exceeds its preset value, the distance between the tip and the sample is increased. If it falls below this value, the feedback will decrease the distance. So I explained these things earlier, but I'm just summarizing. The tip is scanned line by line about the sample surface following the topography of the sample. So brief overview of the tunneling current. The tunneling current flows across the across that small gap between the tip and the sample, a case that is forbidden in classical physics, but that can be explained by a better approach of quantum mechanics, which allows tunneling current. And you can't explain it in classical mechanics. You need quantum mechanics to do that. And tunneling current has very important characteristics. It depends exponentially decay with the increase of the gap distance, and very small change in the tip to sample separation will induce a large changes in the tunneling current because it's really, really sensitive. And this has the consequence that tip sample separation can be controlled in a very precise manner. The tunneling current is only carried by outermost tip atom, and the atoms that are second nearest carry only a negligible amount of the current. So the sample surface is scanned by a single atom. Right. The next family of scanning probe microscopy is the AFM. AFM stands for atomic force microscopy. So AFM was developed when people tried to extend the scanning tunneling microscope to investigate the electrically non-conductive materials like biological samples. Now, in the SPM, it was like crucial to have both the tip and the sample to be conducting. But here, if you have a non-conducting sample, you can use the AFM where we use the atomic forces. Right. In 1986, Binning and another scientist demonstrated for the first time the idea of AFM, right, using ultra small probe tip at the end of a cantilever. And in 1987, luckily, a Sri Lankan is included. Vikramasinghe et al. And the group developed an AFM setup with a vibrating cantilever technique, which is published in a Journal of Applied Physics in 1987, if you want to go and check. And it uses the light lever mechanics.